It's my pleasure to announce the gentleman from Viewdle. They're a startup company with 2 locations, one here in Santa Monica, the other one is in Kiev, Ukraine, where they are able to catch one of the best PhDs around, and that fuels some of the algorithmic work. Who's with us today to present is Laurent Gil. He's the president of Viewdle. And then we have the CTO, Igor, and together they will go through this presentation. So I'm looking forward to it.
All right, thank you, Hartmut. So we are very, very pleased to be here, and we are very honored also to present in front of our friends at Google. You know, when we told some advisors we were coming here, you know, they said to us, "Oh, they're a bit scared, you know, this is Google." And they told us, "Oh, it's like you sleep in a zoo, but all the doors are open," right? So we still decided that we wanted to show you the hard work that we have done for the past 2 years, and we're very proud of it. So, and we want to share this to Google, and we'd like to have all your point of view, comments, and questions at the end of the presentation. What I'm going to do, I will show you what it is that we've been doing, working like dogs for the last 2 years between Kiev and Los Angeles, Kiev in Ukraine and Los Angeles. And then I'll show you a demo, because that's the best way of showing the product, so you see what it is, you see how it works. And then Igor Anshishkin will explain to you how it works. First, my co-pilots here. So I have Yuri. Yuri is the CEO of the company. Igor Anshishkin is a CTO co-founder. And then we have Alex, who actually wrote the stuff you will see. He's a head of engineering. He's a very talented programmer. About Viewdle, what are we? And what it is that we do, and we've been 2 years of our life in this. Viewdle is a set of technologies and products so that you can find people in videos. This is really what we do. This is the core this is the reason why we wake up every day. We find people in videos, meaning that we're able to identify celebrities or friends and families within any kind of video format, whether it's professional content or user-generated content. And we'll show you examples of both of things. It's a little bit further than this. It's not only we find people in video, but we know people in video, which is a kind of byproduct of this, but it's really the big asset, one of the big assets of the company. We know people in video means that we are building a people database. We are building a database, an extremely, extremely large database with millions of people that we can identify in their videos. This is really what we're doing. And we are doing it in a way that is scalable, that is accurate, and that is fast. And Igor will explain how we achieve this. And by the way, the fact that it's scalable, accurate, and fast, it's really the reason why it works. It works in production. It works with industrial strength environment. About Viewdle, so we are a VC-backed company. We have some of our investors in this room. We were very lucky to work with one of the renowned scientists in visual analysis and structural recognition. His name is Professor Schlesinger. He's actually working for Viewdle since the beginning. And we're also very lucky because we started this company in Ukraine, in Kiev. And thanks to this, we were able to attract a very, very talented team. And 2 of them are here. Very talented team means, you have to see Kiev in Ukraine is an East European city. There is no many startups like we are, especially that is doing very hard technology that we do. And so we start to be very famous. We start to attract very, very good talent in Kiev. We have 27 engineers. We have 6 PhDs, and PhDs in mathematics, in computer science, in visual analysis. We are very, very happy and very lucky of having this team. It's a very big asset for us. We are a US company also. So we have four patents in the US, and we are headquartered here in Los Angeles, actually 2 blocks away from here. Another thing that is characteristic of us is you have to see us as really a startup, as it would be in Silicon Valley, but it's in East Europe. And we have the same mentality. We have the same culture. If you go to our office, it looks a little bit like here. We have a lot of young people that are very hard work and that love innovation. And you'll see how it is. I want to show you two examples. One that is coming from the professional world. It's a work we've done with Reuters, so it's all about news, video search in news. And then I'll show you another example that is a very interesting one, how we can apply this to user-generated content. First, about news. This is the web page we developed for Reuters. And the typical example of this as news is, I want to see someone speaking about a subject. In that case, and that's what I will show, I want to see George Bush, he's famous, speaking about national security. And now I've been looking at about 10,000 hours of video clips we have from Reuters. And this is all the results coming from Reuters on this subject. Let's just take one here. It's George Bush probably speaking about Zimbabwe.
Appear to be a sham.
Here he is. There's a couple of interesting things in this example of video searches. Remember what I was looking for as a consumer. Bush, national security. What I get here is a clip of about 1 minute. But you can see on this clip, I started to watch the clip 1/5 ahead of the start of the clip. The reason is because that's when he is on screen. And that's what I was looking for. We think this may change a little bit the consumer experience of video search in the sense that I am not looking anymore at files like you would do in Google Video. You look at files 5 minutes, 4 minutes, and you have to watch the whole thing. Oh, yeah, Yahoo Video is the same. In our case, we can actually bring you directly to the clip that you're looking for, regardless of the length of the clip. And we think this is changing a little bit the consumer experience in the sense that you jump directly to the place you're looking for. And think of a video as a cube with many dimensions. One is image, the other one is soundtrack, and then you have also textual information such as the title, any kind of tagging. What we are doing really is the intersection or the fusion with all these dimensions. So it's not only that I want to see someone, I want to see someone about something. The someone comes from visual analysis. The something, in this case, comes from transcript or speech-to-text. Or tags that is around this video. And the fact that you have a fusion between all these dimensions is really what provides the accuracy that you've seen here. I'll show you another example on a good speech-to-text. This is this one.
Congress needs to move forward with the Colombian Agreement, and they need to approve it as quickly as possible. Approving this agreement is urgent for national security reasons.
For national security reasons, which is
our strongest allies.
Which is what I was looking for. So it's not only that I bring you the clips that are relevant, I bring you to the place of the clip that are relevant. I also can make a preview of what I'm looking for, centered around these keywords of the story of national security. A few seconds before, few seconds after. What this is the following. Think of, you do a search on Google, google.com, and you look for websites. As a consumer, what do? You read the title of the website. Most of the time, you read the 2 lines of previews, right? And then you find out whether these 2 lines of previews is the website you're looking for, and if it's not, you go to the next. We can do the same for videos. This is a preview of the topic you were looking for, about the person you were looking for. This works very well, I would say, on the short tail. I mean, Bush is a famous guy. But it works also very well on the long tail. I'll show you an example here on Google. I want to see Li Miao Miao. She got her 5 minutes of celebrity in the Beijing Olympics. This is Li Miao Miao. I have such a massive information on Li Miao Miao that I'm actually the first on search page of Google. This is really, really the long tail. Nobody knows about Li Miao Miao except the one who is looking for her, right? And this is me. This is the page we have that we did for Reuters. This is Li Miao Miao. Here she. What is interesting with this technology we have developed is it works very well on the short tail, but I would say short tail is easy because you have tags of George Bush, you have tags of Obama, of Angelina Jolie. Working with the same degree of accuracy on the long tail is a lot more difficult. And because we produce such massive amount of information on a video asset, we're able to inject this to traditional search and be relatively in the front of search, as you saw. Now, think of this kind of demo as this kind of technology for your personal use. So the example is, I don't want to see George Bush anymore, but I want to see my mother. Last Christmas, right? I have tons of videos on my Picasa, and I can't find anything anymore. There are just too many of them. We can identify your mother in your videos, the same way as you can do that in Picasa for pictures. But it goes a little bit further than that. Imagine that I want to see Igor in a party last night, but I wasn't there. But I have a friend of Igor who took a video of Igor, and our common friend put this video in Facebook. So we have a Facebook app for personal media, and this is the dashboard of our Facebook application. This is application of exact same thing for the personal media. We're very excited by this because it's probably one of the very first time that you can effectively organize and share videos based on who is there, based on your friends and family. What is very cool here, and this is an example, is this one. This is Sofia Besiekov. She just joined the company. And I have one video of Sofia. But what is cool with this is I have 5 other friends that have also a video of Sofia. And we're all friends. It's Facebook. We're all part of the same social graph. So suddenly, with our kind of technology, I can start to see my friends in my friends' videos. And then the next step is every time a friend of mine posts a video where I am or where a friend of mine is, I receive a notification of this. And I start to watch them. So we think this is probably one of the very, very good tools so that you can organize your personal stuff and you can share it with the people that matters. In this case, the people who were inside the video. And this is very, very hard to do because we think this is the extreme long tail of a video search. And Yigo will explain to you how we cracked this and how we did this in a very, very effective way. Other type of I have to go back to my screen. Sorry, to my presentation. Here it is. Other type of application for this, you can imagine, is security market. You know, once we have people database, and we can start to find you in other location. And some people wants to have this for the security, for some security application or content filtering. We are a startup, so we are not focusing on this yet. We are focusing very much on the first two, which is business solutions, bringing this type of product to media industry, and consumer with video friends. We are developing at the same time with consumer an application that is very targeted to advertising. The answer here is it's very hard to do advertising on UGC because nobody knows what the UGC is about. Many times we get these comments from advertisers. In our case, our job is precisely to understand what the UGC is about. We know who is inside. We know what they are talking about in some cases. We know their profile because it's all linked to our social graph, to Facebook social graph. So we know they are all teenagers. They're all from the same class. Then you can put a Nike advertising on top of it. Now, how we achieve such kind of result, and this is what Igor Anshishka is going to talk to you about, is technologies that are coming from different angles. One is, it's not enough to have face recognition when you start to work on a very, very large, massive scale of people. you have to use other dimensions of the video in order to increase the probability of positive recognition. And we call this the fusion engine. The fusion is we're using speech-to-text, we're using optical character recognition to kind of guide us or help us understand what the video may be. And then the face recognition engine is being adapted automatically based on an increase of probability of other dimensions around the video. And this is what Yigo is going to explain to you. Yeah. Publish.
Okay, we finished at that point. I hope you can hear me. Good afternoon. So as Laurent already mentioned, Fusion engine, how we call it, is very important for us. And the idea is that very early in our development, we understood that there is no technology which can handle the problem as we formulated it by its own. Even having very good facial recognition and video technology, you cannot deliver the experience you want for video search application. And having only speech-to-text, you have Gaudi, you know this very well. Having only speech-to-text, you cannot deliver the experience which consumers expect from an ultimate video search application. So we, being a startup and being very limited in resources, we found a way to integrate various very different pieces like speech-to-text, speaker separation, analyzing existing metadata, and of course our secret source, face recognition and video, to integrate all this into a single system which can produce very accurate results in face recognition and then give out these results in various applications. So when we say fusion typically we understand multimodal recognition when face recognition and, for example, voice characteristics work in concert to help you recognize a person. But we are looking at this more broadly. We don't limit ourselves to only multimodal recognition and actually taking recognition decision. We say, okay, fusion is also when you use various sources of data to speed up training of your database. And this is very important because this is still supervised learning. It's a little bit work ahead to get it to a level of completely unsupervised learning. And this is one layer, level of fusion. Then you have, of course, multimodal recognition, and you have something you can call fusion on UI level. The example which Laurent was showing to you when speech-to-text results are merged with facial recognition index to produce just better experience on screen for video search is exactly fusion of indexes inside search. It's not just that we better recognize person using speech-to-text. So we tried many things, and basically I don't want to bother you in saying how exactly we did that, but a couple of recipes which I think you may use in your daily practice in Google is that, of course, you treat every source of information as probabilistic. I mean, if 2 years ago someone would ask me what's the probability that the caption would be the same for the anchor, I would say probably close to 100%. Now we know that it's far less than 100%. And this situation happens, as you see on screen, not because TV channels make their mistakes, but because just captions typically last longer than face on screen. So this is a pretty, you have this situation pretty often, and you have to account for this. For various sources like Bloomberg and, for example, BBC, you have different distributions. Then, of course, getting this probabilistic aspect, you have to know various distributions around your sources. And there are plenty of them. I believe you can invent dozens. So just to give a small example, let's track this point between the eyes, how it's distributed on the screen in time. So that clear peak, this is a Bloomberg channel, this clear peak in the center, of course, shows that anchors in studio do not move much. They're fixed, and the camera is fixed. So they spend most of their time just sitting in the middle. But what is interesting, I think you can get what are these two small peaks on the left and the right side. This actually corresponds to a regime when two anchors are talking to each other. And this happens on Bloomberg specifically pretty often. So all these characteristics are useful when you fuse probabilistic sources of information. Then the lower graph is distribution of distance, intraocular distance for the same Bloomberg channel. So as you see, in our environment, when we analyze TV content, it's about 60 pixels between the eyes. And then knowing this distribution can help you in second task, which is you have to introduce confidence levels for every recognizer or detector you have. If you have a detector or recognizer which just outputs results, like for example, if you take Sphinx and it just outputs speech-to-text results, you don't know actually what's the confidence level. You assume that if the result is there, that it's 100% accuracy, but it's not good approach from engineering standpoint. Every result has to have some confidence level, even if it's just gradual. So again, let's say face detect. You have no confidence initially, but using even this distribution, you can introduce very simple confidence level. Like for example, what's the probability to find eyes, if it's eye detect, or face, if it's face detect, on the very edge of the screen on Bloomberg channel, say on a right down corner. I mean, if you don't have confidence from face detect itself, you can take this distribution and think about this as confidence. And then when you have confidence level, you try to fuse only high confidence results. High confidence meaning something which is 60% plus. You don't try to fuse many 20% confidence. Obviously, this will not give any good results. I mean, we tried. And the fourth recipe is very simple. You're in a good position here. You have immense amount of data which you can use for actually checking the accuracy of your fusion. So try to check it on everything you have, because sometimes fusion works very well in a limited set of data. Once you get it into production, you find another small piece of data where fusion produced very bad results, and you don't want to roll back your production system to the previous version. So you test on as broad data as you can find. Of course, in our task of people recognition and video, we have to know what's the actual distribution of people on screen. So to say that American television is a long tail, it's actually to say nothing. Like we have almost, 2% of people who appear on screen cover 99.9% of on-screen time. And this doesn't mean that the same distribution you have in search queries in Google. This absolutely doesn't mean that. It just means that American television is very much celebrity focused. But once the TV channels get this content online, they found themselves in a big search engine optimization trouble, because people go and Google themselves, and if they were in video, they expect to see themselves in video. And this is a typical query. I mean, I Google more often, my colleagues, myself, my business partners, more often than Britney Spears and George Bush. Of course, they take bulk percentage of searches, but anyway, this long tail takes a lot in percentage-wise among searches in Google. And we formulate our problem for ourselves as we want to be accurate on all these people, starting from Obama and finishing with your mama, as we say in the office. So from your Obama to your mama, we want to be the same accurate, even if it's personal, usually see video. So to continue this discussion of this problem, you have input media, which is a real-world videos, either starting from something taken by mobile phone, very low quality, and finishing with HD quality, which you have on TV channels. And these are real-world videos. It's a completely uncontrolled environment. We cannot say to Nicole Kidman, please come to camera, look straight, have even lighting on your head, and don't move too much. No, we just have what we have. And sometimes even if it's digital channel, it has very poor quality like this, and you still have to, at least you have to be stable on these results. And if phase detect works, it's even better. Sometimes you can recognize faces like that. And of course, our objects, people in the video, you cannot predict what they do. The facial expressions, the variety of head poses, sizes, occlusions is immense. I mean, the microphone, the hands, the haircut is typical stuff which you have to deal with and figure out what to do with a cluster which has a cup near eyes. You have to treat it somehow. So this is a media. What are requirements for our system in terms of output? Of course, we want to be accurate on long tail of people. So we said that we want to have precision on 95% on all content and recall of 65% at least. We don't use false accept rate as a characteristic that's unusable in our case. And we want to analyze, we have a ambitious goal. We want to be able to analyze all world's television and to be able to analyze personal videos. Imagine this, I mean, in Picasso you have a lot of personal videos in the albums. So to be able to accomplish this, of course, you have to be very scalable, fast, and very reliable. So we achieved this level, and I would like to give a little bit more about what we have. So first of all, how you can achieve this fast, reliable, scalable results, you have to use a lot of algorithms which work in concert, which help each other. There is no single magic silver bullet algorithm which will handle all face recognition, or let's say even all detection. So you have cascaded detectors, and that's how you can achieve, first of all, fast and accurate recognition, detection and then recognition. The same applies to recognizers. As in any object recognition technology for video, we have clusterization piece, which picks up frames with the same person on screen, and then we recognize this cluster versus the database of people which you have. And database is something we call 2.5 dimensional models of the head. So we compare like the cloud of frames to a model in database. And of course, this involves feature point instruction and a classifier and so on. Yeah, so there are several very interesting pieces which we use to speed up the system. How we can get sublinear performance between time spent on recognition each person and the size of database. So what happens if you have 100,000 people in database? You cannot run 100 times slower. This is achieved through, again, cascaded recognizers and something we call hypermetrics, where we don't have to go through all database to compare each face to every face in database. Obviously, this doesn't scale, doesn't work. So we compare to a very small, limited set of faces from the database. And this applies cascaded approach and effective fusion formulas. Just to give you an example, we started to index a channel. We had 2,000 hours, and face recognition taken alone was capable to pick up 12,000 clusters, to recognize 12,000 clusters from these 2,000 hours. And this was less than 5%, this was less than 50% recall, which was not that we wanted. So we fused it with OCR. Face recognition video and OCR, that's a very good coupling. And in this case, it gave us almost 30% boost. This system together was capable to recognize 17,000 clusters. Yeah, cascaded detectors. This doesn't mean that every detector has to give out perfect results. If first detector in face detect cascade give out this as a face, no problem, because there is a second detector which is slower but more robust, and he will filter this out. This is not a face. The second detector can say this is a face. Again, not a problem. It can assume this is Arnold Schwarzenegger, but it's not a big problem because we have a cert detector which says this is not a face. And once you detected everything well, once you collected very good, thick clusters, picking up, for example, one cluster of McCain from 50-minute speech, you don't know that this is McCain yet, then you come to an essential problem of recognizing this cluster versus a very big database. So here in Scalability, we separate two kinds of problems. Accidental, like engineering problems, which you have probably in other applications, like how to get your engine very multi-threaded and how to speed up sometimes using low-level instructions, how to make your UI very fast for a query which runs through the big database. Oops, I'm sorry. And there are essential problems where you have a huge database and how to differentiate Lech and Yaroslav, who are prime minister and president in Poland, and they are twin brothers. Inevitably, once your database is growing, you will find situations when two people look alike. They look similar. So it's very hard to invent a system where triangle inequality rule works. It doesn't work in this case, so you cannot get just a binary tree and keep it sublinear. It's not that simple. So hypermetrics technology is exactly about this, how to make our classifier to be almost triangle, let's say, to make classifier where triangle inequality rule almost is true. It's almost true, but it's not exactly true. And that's how, using this hypermetrics technology, we achieve the thing that we can recognize currently. Each cluster is recognized versus 36,000 people in database, and we keep 95% precision. The final characteristic which we try to optimize for UGC case is how quickly you can get system educated. That's why I was saying that fusion on a training level is also very important. It's how many tags you have to do to train system to recognize your mother. How many tags, how many minutes, how many seconds your friend has to spend on screen, and you have to tag him, so next time he'll be recognized. So here we have some threshold of 60% recall, and right now we achieved very good results. We will have it in our application in Facebook. So I think we achieved the threshold where it's worth for end users, it's worth taking tag efforts. It's not 40 tags per person to train the system to recognize friends, family. So next time on screen they are suggested automatically. We also continuing our research. One of the things we are currently doing is pushing up recall on very low quality videos which you have from a mobile phone. It's not an easy job because feature point detection doesn't work well on low quality image like you have 320 by 240 image. Just to present you one of the ideas which we are checking right now, like you have to be very creative when you have this kind of confined environment. So one of the ideas is, professor said, okay, what the contours which you can play around in the Adobe Photoshop, they, like, I will just show you and then explain. They work. Oops. No. Okay. I really don't know how to take all this. Okay. So this is the feature point of eye and how the contours are growing around the eye. So we say the following. Let's define a feature point as something which is surrounded by maximum numbers of contours which are included into each other. It's pretty novel approach. And because contours they do not depend much on lighting, and they're purely defined by shape. Of course, the contours themselves changes, but how they're included into each other doesn't change much. So you can get a graph of contours included into each other. And so the definition of feature point, the feature point is something which is surrounded by maximum number of contours. And that's how you can get an eye, in this case, nostrils, mouth, and so on. And this, you don't need to use this on images of very high resolution, but this is very useful when your resolution gets smaller and smaller, when you have a face of 50 by 50 pixels. So we will include this, this detector as one of the detectors in a cascade. Then, of course, the holy grail, getting 3D shapes from two-dimensional images. We will also work on this, but under slightly different angle. We don't try to use this in actual recognition. We try to use this to speed up training, because sometimes, especially in UGC, you have just a couple of tags, as you have seen here. You have a couple of tags, and sometimes you see person just from, let's say, profile view, and you cannot get the complete model. So you have to use 3D here with even some, let's say, average 3D man to complete the model, to to produce faster education for the system, to increase the probability of good suggest next time this person will appear on screen. And of course, body tracking and the detection and tracking. We started this just as one of the detectors which can help face recognition. But then we find a potential client who said, okay, I want to apply this to sport videos. I want to track football players, soccer players, and so on. And, and we think that this can be very well, because we started from premise that camera is moving. Camera is not mounted still. This is a solved problem. Camera is moving sometimes even faster than the object. So you consider object as almost stable compared to, for example, if when camera is rotating, your environment can rotate faster than the object just pixel-wise. So face detection technology will be also built in some future. And I think that's it. If we want to add something.
Just to finish, what I wanted to show you is a live running of the engine. As soon as it comes, you will see actually the engine running live, and you have a flavor of how everything that Igor told you does work. So here I have a number of videos. I'm running the first one, and let's see. This is the engine working on this laptop, so it's not designed for this, so it's a bit slow. But you will see the engine running, recognizing someone in the video. Here it is. It's me. It will say, I hope, that it's me. Now the engine, here I am. What is cool with this demo, with this video, is it was taken from a mobile phone. In this case, it's N95 Nokia. And we would love to do this on Android. I think I saw one G1 somewhere. So whoever has it, I'd love to have a look at it.
So we hope application API will get us access to camera.
We have developed our uploader on mobile phone. This is really experimental. This is 2 weeks old, so we've been playing a lot with it to see how it works. This is very hard to do, because that's the kind of the ultimate UGCs. You don't know anything. You don't know the lighting condition. You don't know if you're inside, outside. You don't know if you have direct light or light on the side. And that works pretty well. So that's a kind of, to show you it really works, how it works in real time. So what we show you is, you've seen a little bit of what we've been doing, and we spent a long time, believe me, on this with all our team. And Igor gave you some flavor of how it works, what were the challenges, and how we overcame this challenge. So if you have any question, we'd be very happy to answer you. And it's really an exchange, so we really like to know what you think about this, and how this applies to solve all the type of problem that you may have. Thank you. Join us. Yes.
One of the questions I would have, how large is right now your database of models, face models against which you match the videos?
The question is, how large is our database of faces to match videos?
Face models. Megabytes or number of people? Not number of people. So for professional, we don't mix professional.
We don't mix professional videos and UGC, so yet, right? So professional videos is currently 36,000 people, and UGC, I honestly do not know. It's a couple of thousand. It's not millions yet. We haven't launched the application really.
That may be a related question. Could you give us an idea how much data, let's say video frames or so, you would need until you feel that you have a model of good enough quality to reach reasonable recall?
That's a very good question. That's exactly why I deleted the y-axis. So we feel that we suddenly push the limit up to less than 10 tags, 10 manual acts, to keep it up 65+% of recall. So we are working to reach the goal of, our goal is 3 tags. So 3 times I'm ready to say this is my mom, and then I expect then expect my mom next time on screen will be recognized. So I can say that this goal is reachable with the face recognition in video. Still images, honestly don't know. Ria tried it. Maybe you will tell us from Picasso experience. But in video, this is achievable.
I like the measurement, so that number of human interventions.
Yeah, yeah.
More
because that's costly, right? That's your real cost. More questions, please.
Do you have a question in Mountain View?
I haven't heard. Can you repeat louder a bit?
How much data does it take for each individual to recognize roughly?
Oh, I think.
What's the question?
How much data per individual have in a database?
How much data for an individual to be recognized?
What is the size of the recognition?
In kilobytes? In what? In frames?
Just how many kilobytes of data do you store?
It's up to a couple of megabytes. It's not much.
When we try to recognize?
Go ahead.
So, correct me if I'm wrong, I will try to repeat the question. So you're asking what's happening, how many recognitions do we have once we collected faces from video, right? So as I mentioned, we have clusters collected from video. So clustering technology picks up frames with with the same person. It never mixes up 2 persons in one cluster, but so we have, let's say, cluster 1, 2, and 3, and this will be person 1, person 2, and person 3. And then we do recognition of cluster 1 versus database. In the process of this recognition, we have, let's say, pretty complicated process, but there are several comparisons, of course, of, let's say, picture-to-picture, if you wish, comparisons. But it runs fast, and most importantly, that it's sublinear with a growing size of database. That's the most important characteristic. Even if this individual recognition may take 200 milliseconds, it's not a big problem as long as you have to make only 1,000 comparisons or 500 comparisons for the whole database. And then there is the question how to narrow down number of comparisons if you have 100,000 people.
It's sweet to see the number of faces you found in a photo. So say you find 5 faces in a photo, we identify that there are 5. And then FR starts to recognize to see whether or not which of these 5 are actually predetermined as tagged or recognized, and then we label them. But that's like, it's a slow process, at least from a web standpoint, because when you scan a photo, you have a couple seconds that they recognize that you stop. But in a video form, it's frame by frame by frame by frame.
This is a clusterization is a very fast process. It's not scaling, right? It's linear. I mean, you have to spend X minutes to clusterize 5 minutes video. It can be like 2 minutes, right? But I mean, this happens fast, and then you try to recognize it versus the database. So it's also a question of how you position this in your user interface, right? I don't know what's the delay between the moment I'm posting a photo and the moment when this photo is already grouped with others, so I can tag it. In our case, clusters are growing as video goes, and you can basically switch on comparing cluster to database at any moment when you like. It's just a matter of probability. What's the probability that this cluster will be positively recognized? If it's the probability is highest when the cluster is the biggest, right? Biggest what you have.
Technology. If I took a photo of you and then I labeled you, and so the system knows that it's a photo of you. But then for whatever reason, either you rotated the photo and then you rotated it back. We have the ability to detect that there's a face in the photo, but we don't have the ability to automatically detect that that's you and there's a face in there, and oh, by the way, it's this person's name. We have to relabel the name each time when there's any changes to the photo because we don't have that technology to automatically find it.
Oh, this is not a case for video, because clusters are the same if you supply the same video, even if you, let's say, it's semantical technology. So even if you, let's say, downscale it, reduce the resolution, there is a very high probability that it will be almost the same cluster, and it will be already recognized, for sure, if you recognize previous cluster. So if you supply the same video, it's 1.0.0 that it will be labeled correctly. We haven't even beat exact IDs in clustering.
Yes.
Yes.
By the way, just this is our Facebook application. So this you can see how you can move around a video once it's tagged. So you have in the bottom here the people who are in the video, and you can same way you can jump to a place on professional content, you can do the same on UGC. So we encourage you to come and join us in Video Friends application on Facebook, so you can play with the application. It's open application right now. Any more questions?
Thank you very much for coming.
Thank you.